course, probably you wanted me to record in the past, right? You wanted to record all the stuff I just said. So
No,
now,
it's fine.
yeah, you have now I've recorded myself saying that you would need to record the
It's
stuff.
fine. It's just that my network is breaking, so I don't want to miss anything. That's
okay, but here, so okay, so anyway, but that's the point, and this goes through and illustrates this with combination and element, shows the elementary matrices, and you have all these calculations we've done, and that's basically so what have we done? So that okay, apart, that was the most important thing, the stuff with row operations and their connections to Gauss's method and the giant, and justifying and seeing why the giant augmented matrix method, why does it work, you know? Okay, so and I think we've picked up also the fact that the inverse of a product is the product of the inverses in reverse order, right? So that's a useful, and that's really useful. And the other thing that's in the chapter that we haven't gone over is some of the proofs, right? There's little proofs of things to show that things are unique, say. For example, let's say that you have this idea that M plus Z equals M, right? That's a zero matrix. Well, what if there was another one, M plus Z prime equals M, another one that wasn't equal to all zeros that did the same thing? No, maybe we can't think of one, but let's say there was one somehow, magical way. Well, we could, since this is supposed to apply to all matrices, what we can do is we can say, well, what happens if we apply this to Z prime? We would say Z prime plus Z, this first form here has to equal Z prime. But we can do this form here and apply this to Z and say Z plus Z prime has to equal Z. We've applied this one to Z and this one to Z prime. But you notice then that this is Z prime plus Z, this is Z plus Z prime, so they're equal, so it has to be that Z prime equals Z.
So question here, M was
any matrix. M is any matrix.
Okay, but what's a zero matrix again?
Well, okay, Z, we know that we know that we're saying there has to be a matrix Z, right? We're saying that we're saying one of the properties of addition is there is a matrix Z. Now, let's say we haven't found out what it is yet. Okay, let's say we haven't found out what it is. Let's ask, could there be two different matrices Z, right? Z and Z prime, and from the axioms we have so far, we can see it's impossible. It's logically impossible for there to be two matrices. So if we find one, see if we guess one, we say, look, Z is this one. We know this is the only possibility, and we can give it a name Z because we know it's the only one. It works the same way with inverses. You could think, well, if I know that M inverse equals M inverse M equals identity matrix, what if there was a second one? Maybe there was M inverse alternate, which equals M inverse alternate M, which equals the identity matrix. Could there be two different matrices that I would multiply towards M to get the identity matrix? Well, you can do the same thing, in which you can show that this is, let's see, we have we can start with M inverse equals the identity, right? But we know that we can multiply this by let's see, what do we want? We want
I equals M inverse.
well, we can multiply this equation by MA inverse, right? Okay. And now from this equation here, we know that this equals the identity times M equals MA inverse. Then, so we know that M inverse equals MA inverse, right? And now I just have to turn this around. Oh, maybe you want to do is start it from the other way around. Oh, yeah. So if we start from M inverse M equals the identity, then we can multiply this by MA, M inverse M equals MA identity. That's just going to equal MA. And this, because MA inverse M is the identity, this is equal to the identity times M, which equals MA. And that means that M equals MA. Nope, what did I do? I did something here badly. I don't want M equals, oh, yeah, I don't, yes, okay. I did it right the first time. I don't need this. That was, I got what I wanted to prove and forgot that was where I was going. I mean, that's true, but what I wanted to show was that if there were two, if the idea of showing something unique is to assume there's two and show that they're the same. So I assumed there were two inverses here. And then I showed that M inverse equals MA inverse. So if I suppose there were two, that's logically impossible. There's only one. The other thing is, for example, what's the inverse of the inverse, right? Well, the question is, if I can take M inverse and I want to find the matrix and multiply this to get the identity, well, I know that this works. Since the inverse is unique, this has to equal the inverse of this one. In other words, this can't be a different matrix than this, because all inverses are unique. So I know that M inverse times M inverse inverse equals the identity matrix. So what is this? Well, I know this is true. So M has to equal okay, these proofs are written out. I mean, I've gone over them too quickly, maybe, but there's little proofs here that are all based on the properties and it's the strategy. If you want to prove something's unique, you assume they're different, then show they're the same. And I've written it out with words in the text. Not part of the transpose. Then, yeah, here's the, let me see. Not that one. Yeah, here's the, see, A inverse itself is invertible with A inverse A equals A. So here's this proof of this fact. And then AB is invertible with AB equals B inverse. So here's the proof of both of these facts laid out where without more carefully written out than I've said it in words verbally. Okay, so just this little paragraph here is the proof that these are true. You can see let A and B be n by n invertible matrices. A proof is like a play, right? When you have a play, you have characters that come on the stage and they call each other by their names, you know? So the same way you have to sort of, the first thing in any proof is you introduce names for things. Then since they're invertible, an inverse of A inverse, we call it Q, must satisfy this property here, right? Comparing this with the property resulting from A being invertible shows that such a Q exists with Q equals A. Now, since there's only one matrix A that satisfies this because the inverse is unique, we know that the inverse of the Q is equal to A. So anyway, if you read through this and here's the calculate, we sort of did this. Okay, well that's, and then here's the one where you have all of them. Now here is, we can think about why this is true, this invertible matrix theorem here, which connects up the different concepts of invertible and singularity. So you have four concepts. S is invertible, a square matrix has an inverse, is logically equivalent to the statement, the reduced echelon form of S equals the identity matrix. That's what we used before. The idea is if it's invertible, so if you think of it through the giant augmented matrix method, this is going to be true. And then here's the two questions with singularity about single solutions. Okay, well let me since I think I've lost your attention, we can go and now practice. Let's see. Oh, there's one topic we should mention, the transpose. If I have any matrix, say M equals 1, 2, 3, 4, 5, 6, like this, doesn't have to be square. There's another matrix that's the transpose matrix where I interchange rows and columns. So the transpose is going to be the first row becomes the first column, the second row becomes the second column. Yes.
How does this help?
How does what help you? The transpose?
Yes.
Okay, later on, we're going to, it's like transposes are you can see how inverses and stuff are important, but the question is, why is a transpose? It changes the matrix, right? I mean, this, what do you mean?
2 by 3, 2 by 3.
Right, exactly.
But why do we have to manipulate that way? So what kind of condition? That's what I don't understand.
Later on, when we're using matrices to represent maps between systems, interchanging rows and columns has to do with interchanging, like a map goes from space A to space B. Interchanging rows and columns is going to be like a map from B to A. So it's going to play a role with maps. It plays a minor role. It also plays a role when we come to determinants of square matrices. So it's a simple. So yeah, the transpose is defined even if it's not square. Interchange rows and columns. But let's apply it to a square matrix. S transpose. First row is first column, second row is second column. Well, you notice something, for a square matrix, the long diagonal didn't change, and I just swapped across this way, right? So so another way of doing a square matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. A transpose would be where I just keep these the same and swap these two, 4, 2, 3, 7, 8, 6, where I just sort of, it takes the upper triangle and sort of flips it. It sort of flips it across the middle, right? This works for square matrices. It doesn't work so well for these ones. So this is just.
So the crisscrossing.
Oh, this is.
9, 3, 5, 7, given the same.
Oh, something I didn't flip here. This is 3 and 7, right?
Oh, you told me.
Because I'm supposed to flip those, but I didn't. So you can see first row, first column, second row, second column, third row, third column. Anyway,
So only square matrices have inverses.
only
So,
square matrices have inverses, but all matrices have transposes.
So it doesn't, even if we have the same number, let's say, of number or matrices for the,
Right,
like if it's 16, 24, 35, 36, whatever.
right.
The first diagonal from A11
Yeah, the long diagonal entries
remains the same
remains the same
for all of it.
for all of them, no matter how big.
Wow.
And then corresponding ones are sort of reflections on that long diagonal. They're just gonna be sort of flipped. So you can sort of think like this one's gonna flip with this one with this one, this one with this one. But that works for square matrices. It doesn't really work so well for this one, right? For non-square matrices, because here they're different sizes, and so
Yeah, but I would suggest that this one's easier to observe and understand than the first.
yeah, that's the definite. So if I take entries, right, it's really simple. Okay, if I have a matrix A with entries A, I, J, and I have a matrix A transpose, then A transpose I, J just equals A, J, I. I just swap the indices, right? So if I goes from 1 to M, and J goes from 1 to N, the same thing is true here. So if this is an M by N matrix, this is going to be an N by M matrix. So this swapping of indices works even if with these same restrictions, this will you just have to swap the indices and you haven't. So this form is really compact for doing transposes.
I would not, like, another way, cannot find it by your protocol.
Excuse me?
Not like find.
The reverse order.
Yeah, because like if you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 8, 3, 4, 3, 1, 4, 3, 2, 5, 8.
Yeah. This one if I had a big matrix, I could use this to find an individual transpose element. In other words, if I wanted to find what A transpose 1, 3 was, that's going to be A 3, 1. Okay.
So after you the hypothesis from which hypothesis
No.
what is that for?
The transpose.
Transpose. So they are 1, 2, 3, 4, 5, 6, 7, 8, 9. If you transpose it, the first one that we have 1, like from the first column we have 1, 2, 3, and the next numbers of the order are plus 6. Like we have 1.
Oh, that's just an artifact of.
Okay.
It doesn't matter about it. It doesn't matter. These could be any numbers. I just wrote them because it's easy to write down. Yeah, that has nothing to do with anything.
Because like I just saw that I was like, oh, maybe it's
If there were patterns here, if there was some pattern here, you might see some pattern here that was slightly different, right? But but this definition also means something like what is the transpose of the transpose? Well, if the transpose has A IJ transpose equals AJI, then the transpose of the transpose is going to have elements IJ equals a transpose JI, which equals AIJ, so that the transpose equals the original matrix.
Question, I have 2 questions. Is following statement true? Only non-singular matrices have inverses?
Yeah, non-singular, that those are logically equivalent. being non-singular and having an inverse are logically equivalent.
Good. And then only square matrices, or only,
Only square matrices have inverses, only square matrices can be singular or non-singular.
okay, so non-singular matrices must be square.
Yeah, the concept, singular matrices have to be square. The concept doesn't apply except to square matrices. If you have a non-square matrix, it's not going to be singular or non-singular. It can have more than one solution, or
So it won't be singular, non-singular, won't have determinants, or it won't have a inverse if it wasn't a square matrix,
if you were asked,
and any of
the
those
question to
properties.
ask is this 1, 2, 3, you see, 2, 5, 6. Is this matrix singular? No. Is it non-singular? No.
The singular is the only.
So it's only,
singular is the
only when you have square matrices that see, here is no and no. For a square matrix, it's going to be either no, yes, or yes, no. Right? In other words, 1, 2, 3, 4 is either singular, in which case it's either not going to be it can only be, it's going to be one or the other, but not both, right? If this one is if you ask, is this matrix singular? And you say no, and then you ask, is it non-singular? The answer is yes. So this is, maybe that's better. Singular, non-singular, right? If you answer no, it's not singular, then yes, it's non-singular. If you answer, is it singular? You say yes, then you say no, it's not non-singular.
Singularity property of square.
Right, exactly. So that leads to some, like, I think there's a regex question when you're out, you have list all the singular or non-singular matrices, and I give you a non-square one, to which, so you don't want to include that in anything. Okay.
What does singularity help us understand?
The idea is that we want to know, say, for a linear system, when do we have a solution? And for square matrices, we can say that if it's non-singular, we always have a solution. In other words, the point is this, that if I have, let's say I have a linear system, A times X equals B, right? If A is non-singular, then there's an A inverse, right? If A is non-singular, then A inverse exists, therefore X equals A inverse B. So if A is non-singular, there's always one solution. Right? Now, if A is singular, we don't know. It could be that there's many solutions or no solution, because we don't know. There could be a contradiction, because if A is singular, it could be that AX equals B has no solution or an infinite number of solutions, because we can't invert this, so we don't know what's going on. So the point is, non-singular matrices carve out a case when we know what beforehand where the system is soluble. Now, it's only in special cases, and it's only when you have one solution. So for singular matrices, we're still up in the air, because it could be a contradiction. Now, for if it's a homogeneous system, if AX equals Z and it's non-singular, then we know we have an infinite number of solutions, because if this is zero, there's no contradiction possible. If this is singular, yeah, I got it backwards. If this is singular, we have an infinite number of solutions. No, there can never, there's always a solution.
Oh, there's always a solution in the C.
Z is always a solution. So if it's homogeneous, we always have a solution. So we're going to have an infinite, if it's singular, we're going to have an infinite number of solutions. If it's non-singular, we're going to have one solution, namely Z, right? Because if this is the case, I could solve by saying X equals A inverse Z, which equals Z.
Singular and homogeneous.
Excuse me? I'm sorry.
If it's homogeneous and singular,
If there's
always going to be.
Yeah, that's why homogeneous systems are good, because the homogeneous system cannot have a contradiction. Okay, you can look at the properties of transpose. It has the transpose of a sum is the sum of the transposes. And the product of a transpose, the transpose of a product is the product of the transposes in reverse order. Sort of works like invertibility. It has to be proved this is the case, right? It's not obvious. You take
How about the third one, Professor, with that lowercase r? What's that?
Oh, that just says if I see R multiplies all elements, I can change the order of, I can multiply something by R and take the transpose, or take the transpose and multiply by R. It doesn't matter.
So r is kind of like a scalar in a way, like a number.
R is just a number.
Okay,
R
so
is
like
a
you can
number.
you could take the product of a number and a matrix and then take the transpose of the matrix, and then similarly you could take the transpose of the matrix and then multiply that matrix
And
by
have
the
the
number.
same result.
Okay.
This is also not so obvious, right?
Isn't that one similar to distributive property where you just distribute the transposes in, take the
Yeah,
transpose,
sort
and
of
then add the entries if applicable?
Yeah, it's sort of like a distributive operation, but it's like it's not obvious that it would be true, right? I mean, they all require some thought, but the proofs and that maybe some explanations of why they're true are down here. Let's Oh, okay. Here's a question for you. Let's say, suppose A is invertible. That means that A inverse exists. What is the inverse of A to some power? Like, let's do it. What's the inverse of A cubed? Excuse me? What's the inverse of A cubed? Okay, A inverse is not equal to 1 over A. Okay. So you want to know what A cubed, what its inverse is. Okay, that doesn't have any meaning. 1/3 does not have any.
So is it like
you
A
can't
inverse
raise a
multiplied by?
matrix. There's no operation raise a matrix to the 1/3 or taking a cube root of the matrix. Yes, it would be A to the -1 to the 3rd power. Right, you can't, in other words, you could say this was A to the -3, right? That's okay. But the point is, if you can take you can sort of see, if you want to find the inverse of a cubed, you can just multiply the inverse together 3 times.
So if for example, if I had an A inverse and you're saying A, because I kind of wrote it down as A cubed and then take the inverse of A cubed, and then I got the product of A inverse, and A inverse, you're saying that's
Yeah.
applicable as well?
Right, because this is, so we can say that this is a to the -3 if what we mean is a to the -1, a to the -1, a to the -1.
Right, so I thought of that as like A cubed, and then in parentheses the inverse of that A cubed, and then I just distributed it like using the properties of exponents. So I just didn't know. So the original way to write it would be that you would have to first do the A inverse and then parentheses cubed. So it'd be
Yeah.
like the cubed, or it'd be like A inverse cubed instead of the inverse of A cubed.
Yeah, the point is I don't have to calculate, I don't have to multiply a together 3 times, then find its inverse. I could find the inverse of a, multiply that together 3 times and have the inverse.
So that makes sense, where you can take the inverse of A first, then multiply it 3 times, whereas the other way you could take A and
Multiply together 3 times, but then I have to use the giant augmented matrix to find the inverse.
to find that
It
inverse.
might be
So
complicated.
you're just looking at a simpler way to, like, a faster way to, but both ways essentially would, like, theoretically go to the right result ultimately, or
Yeah, exactly.
okay.
Let's. Well, it's 1:15. I guess the question is, does anyone have any questions? Maybe if you have any questions on regex or other questions, or you want me to explain something, you want an exercise on something?
For on like
Okay.
getting to the point that
Let me look at problem 4 on. This is assignment 2, right? Here's a system with 3 equations. You mean this one? And
when I get to the end, like I have no favorite.
right,
Especially from the CIA or the other indication, it shows my first row is like on my favorite it's positive.
okay, well, let me copy, so that other people can see. Oh, here it is down here. What is, you get, let me see, this is, you're doing an augmented matrix, right? Rows?
We got 1, 1, -1, 3, 2, 0, -1, 1, 3, 1, 1, 0.
Oh, so this is the original one.
That's right.
Okay, so what's you say you've done some row operations.
And I got to a point that I have 1, 1, 0, 5 over 2,
What over here?
5 over
Oh, 5/3, okay.
0, 1, 0, 11 over 6, and 0, 0, 1, -4 over,
Okay,
and I'm trying to reduce to natural 4.
so reduce from, all you need is minus row 2 plus row 1, right? Because you only need to get rid of this, then it'll be the identity matrix, it'll be in reduced row echelon form.
I missed that.
There's a minus sign somewhere?
What I try to do is like I switch row to row 1. For no reason.
Oh, so you're at this stage, but now you see that you just, if you have this, you just do this. Oh,
Negative,
so you have 5/3 minus 11/6 would equal 10/6 minus 11/6, which equals minus 1/6.
That's why I'm.
Oh, yes, I should point out that on um, there is an application on Vera Virtual called WX Maxima, and if you put in, let's see, 5/3 minus 11/6, it gives you the answer not as a number, but just it reduces the fractions. So you can use this to do all your fractions.
What I did was like, I changed it after.
Excuse me?
I messed it up.
Oh, you said there's an arithmetic problem here, right? Okay,
Because I did both. And, I did the same mistake I did in Simon.
oh, okay.
I did both 2 minus.
Yeah, you did, yeah, because you did what you want to do, you don't want to do,
Yeah, because it's not a roll.
this is bad, right?
You can lose points.
Yes, you can lose points, very bad. Let's see. So, other questions? I mean,
Yes, I could you go like what you're expecting from us
what?
on 6 and I believe it's no 7 and 8.
On the assignment?
Yeah, like
Oh, what you're supposed to do here?
and stuff because
Okay, so let me. Oh. Oh, no, oh. What am I doing? I want to. There. I want to be able to read all of it. Oh, I need to bring this in. There. Okay, so for 7 and 8, you use elementary row operations to arrive at row echelon form without reaching reduced. So we use, so you just get it so it's echelon form and identify the leading and free variables, just like we did in assignment 1. Then you find the particular solution since you know what the free variables are, you can set all the free variables to 0. Oh, so maybe if I do an example, like let's say that I have the system 1x plus 2y equals 3, and say 2x plus 4y equals 6, right? Then what are you going to do? Well, you're going to follow these directions. You're going to make this, you're going to look at the augmented matrix 1, 2, 4, 1, 2, 2, 4, 3, 6. You're going to do the row operation -2 row 1 plus row 2 to get 1, 2, 3, 0, 0, 0. That's an echelon form. Well, no, I want maybe that's sort of bad. Maybe I need to do something else. Oh no, I need a particular. Okay, I need a 3 by 3 to be a good example. I need. This is okay. Okay. The problem is this one is in reduced row echelon form and echelon form at the same time. So that's a little bit. Let me make this then a little bit more complicated.
okay, what if you solve and you have this, is that wrong?
Let
If
me
you have something that is in a row echelon form and reduce row echelon form at the same time. Is it wrong?
Equals, how about this system? The problem is I want something that gives you the example like let's say you had this system here, right? X plus 2y plus 3 equals 4, 2x plus 5y plus 6 equals 9. The augmented matrix would be this. Right? I would put it into echelon form by minus 2. Oh no, I don't want it to be in reduced or echelon form. So we're going to do 6. Let's do 8 there. Okay. Yeah, okay, how about this? So this will be 6 and this will be 8. There's the so we do minus 2 row 1 plus row 2 to give 1, 2, 3, 4, 0, 2, 2 3s is 6 is 0, and 2 times 2 is 1, right? So it's an echelon form, but not reduced form. So you stop there and you say, okay, well, look, X and Y are leading, but Z is free, right? So you can set the free variables to 0 and say the first equation is X plus 2y equals 4, because we've set Z to 0. And then 2y equals 1. So y equals 1/2. And x equals 4 minus 1, which equals 3. So the particular solution, V particular, equals 3 1/2. That's the solution with all the free variables equal to 0. That says find the particular solution by setting all free variables to 0. So that's Patrick, you have a question?
Yes. So when you took the first example, after solving, it gave you a solution which was at the row echelon form and reduced echelon form. Any of those?
Not reduced, but not reduced echelon form.
No, I'm not talking about this one. I'm talking about the first example you took. So my question is, if you have something that's in both reduced
You're talking about the
echelon form
example
and
that I
echelon
raised?
form, is it wrong? For
Well,
the
yeah,
first,
the first example, the problem is you would get echelon form and reduced echelon form at the same time.
yeah, because I don't know.
That does not happen here. I think, or maybe it does.
I think it does when I'm from my own
Okay,
solution.
but that doesn't, well, you stop there and you get the particular, whatever you do, you're going to get a particular solution, right?
Yes, yes.
So you have the particular solution. Whether you're in, I'm just saying this is the general case. If you get to the same, then you'll still find the particular solution by setting all free variables to 0. Then you go back and you say, okay, well, look, instead of setting that to 0, let's solve the homogeneous form, which is 1, 2, 3, 0, 0, 0, 2, 0. So this is the homogeneous form where I haven't set z to 0, but I've set this to 0. Then I can solve for, I'm going to have x plus 2y plus 3z equals 0 and 2y equals 0. So you're going to end up with y equals 0 and x equals minus 3z, right? So then you know that the set of homogeneous solutions is going to equal z times minus 3, 1, 0, such that z is any real number. Ah, oh, yeah, I do, because otherwise it's contradictory. Yeah, 0, 1, because Z is the free variable. Okay, so then set all the constants in the rightmost column to 0 after the augmentation bar and find all solutions of the associated homogeneous system. So this is, we have the particular solution, we have this one, combine the particular solutions in these ones, so we say the general solutions, a general solution is V would be 3 1/2 plus Z 3 up here 3 and 0. This is missing 0 there. Plus minus 3 0 1. That's the general solution, right? A homogeneous one plus the particular. This is V particular. This is any homogeneous solution. Find all the solutions to the associate. Combine the particular to find the solution of the complete system. Oh, and you could write this as a set also, right? You could write S equals the 3 1/2 0 plus Z times minus 3 0 1 such that Z is a member of R. I'm just trying to get you to see, okay, you could get the system, set the free variable to 0 to get the particular solution, or set the constants to 0 and get the homogeneous solution, then combine the two. Okay. Then you could continue from row echelon form up here to get reduced row echelon form, right? And then just solve the whole system, and you're going to get, and you should get the same result. And the idea was for you to go through that process to just do it two ways. You can compare and see you're going to get the same result. And the problem with the problem is that the directions are harder to understand than to work the problem. So I think I need to work on this problem of doing something a little different, like dividing it up into steps, like ABC, where you do each step and it will. Here you have to sort of sort through and figure out what the right thing to do is, and I realize that's a problem. Okay, other questions? Yeah, this weekend there's going to be a second version of Concept Check 1. And you have a long weekend. There's no class on Monday.
So to confirm, Professor, the Concept Check 1 is going to be up sometime today, arbitrarily.
Tomorrow.
Sometime tomorrow? All right.
No, sometime today. Today's Friday.
I recall you said, yeah, like somewhere around. Okay, so that's fine, as long as it'll be up sometime arbitrarily.
Professor,
And
did you say it was due on Monday?
Excuse me?
You said the concept check is due on Monday, right?
Yeah, the concept will due on Monday midnight,
Oh,
All right, good.
because we have no class on Monday. And no office hours on Monday.
But are you going to open?
Then what? Oh, yeah, there's going to be on also next week, you're asking about, there will be yeah, so the point is, yes, what will also appear on Sunday night will be the RigX problems for chapter 4 on vector spaces here. But we won't, so we'll start that material on Wednesday.
Are we going which assignments are going to be
Oh, yeah, then
Sunday, or it's going to be farther down?
I think it's still scheduled for Sunday. But I mean, there's no reason I couldn't move that. I can move that assignment date for assignment 2 to Monday. That's not a problem.
Yeah, that's how I'm.
So you can think, and you can think that you have, so you want to do assignment 1 version 2, assignment 2 version 1, by Monday night and do concentric 1 version 2 if you need to do it by Monday night.
And let's do Sunday.
The licks can be due on Monday night. You can, I'll change it, whatever it says, I'll change it so it's due on, so you don't have to worry about doing it before, you know. And then also there will be, I'll put up at some time there'll be version 3, assignment 3, version 1. And assignment 2, version 2. But there won't be an assignment 1, version 3. That'd be too much.
Let's check the question about this stuff.
Okay.
So, like, let's say I have -2 row 1, or -2 row 2, plus row 1, and then -2.
Let me write that. Okay, you're saying, saying if you have,
Negative row 2. Plus row 1. And then negative row 2 plus row 3. Is that one?
oh, negative row 2 plus, that's 2 row operations. Even if you put them on the same little thing. Because each one of these is an elementary row operation, and it's fine to do them together because they don't interfere with each other.
So it's fine to leave it like
Yes,
that?
it's finally, and so you would have a matrix here and a matrix here, and you don't need to separate these two, because if you look at this matrix here, row 2 doesn't change, and you just use it to change row 1, and use it to change row 3, but you can just look at this and see whether or not how to do, so you can sort of do it in your head. Or if I'm looking at it, I can sort of see what you've done, whereas if this was like minus row 2 plus row 1, and this was like -3 plus row 2, then it would be all scrambled up.
Okay, so it's fine.
Yeah, that's fine.
So I'm just like,
Yeah, this is fine. Let's see. And what do we have? Let me just make sure that I'm. Yeah, demonstration 1 is on the weekend of February. Wait, what is? February 11th. Let me. Yes, February, yes, so here's this weekend here. At the end of next weekend, we'll have our first demonstration. Where most of those points will be like, just like 85 points out of 100 will be doing licks problems like assignment 2. So you'll have assignment 2 and the solutions assignment 2 to study, and that will be exactly the same. So demonstration 1 will feel like assignment 2, except it won't have that weird problem in the middle. And yeah, and this is really vector spaces, linear independence, basis dimension review. Just before this is sort of these all are together as part 2 before the spring break. Excuse me?
space, null space.
Yeah, vector spaces, rank, dimension, basis, linear independence, subspaces, spans.
Vector, matrix multiplication is just, linear transformation.
We won't see matrix multiplication until we get to linear maps. We won't see. Yeah, A times B, multiplying matrices. We won't see that again until April.
Okay. And maps are just linear transformation?
Yeah, linear maps, linear maps are defined as maps between vector spaces. And you can implement, like with a formula, you could, like f of x equals x squared, there's a formula with one vector to another. But you can implement all those linear transformations with matrices. If I compose two maps, like F goes from A to B and G goes from B to C, and I want to know what map is it from A to C, I can represent those as matrices and multiply the matrices.
Yeah, I want you to multiply the matrices together, get essentially a map from one to another.
Right. And also, we'll be able to
That's
tell the
just- that's
properties
just
of the
basic
map.
spec.
If we have a map and we have a matrix that represents it, we can tell the properties of the map from the matrix.
And that's the basis vectors being transformed because the big ones are different range basis vectors.
That comes down here to projections and bases. Because a basis change is basically an identity map that just changes. So every change of basis is just an identity map. So we have different representations of the identity map implementing changes of basis. And now you're in April 8th.
Big. And like so much related knowledge.
Yeah, we'll do maps. We do, so yeah, so that's the last big topic here, right?
Let me physics topic.
Excuse me?
Let me ask you a physics topic.
Oh, in
You can't fight Robert off. You have to like eat the whole thing.
well, the problem, I think it's more like having one dish fixed in many different ways. It's more like you have like all the different ways you could make pasta or cook something, right? You could bake it, or you could broil it, or you could put it into a stew, or you could fry it. Well, that's like we're taking the same stuff and doing different things with it. Because all these problems will still all solve with Gauss's method. If you want to,
Which Gauss method is just matrix multiplication.
well, with elementary row operations. But we won't see that, but we don't have to, that's mainly, yeah. We don't see those again until here. Because this, see, we have matrices here. This is a technology of matrix arithmetic, but we don't have matrices again until April. We will see matrices in yeah, we see, we don't. Well, you have augmented, you have the matrices from, well, that's not quite true because you have the matrix form of equations, and then we'll have another form called the vector form of a linear system rather than the matrix form.
Vector times x plus the vector times y.
No, it's like this. If I have 1, 2, 3, 4, x, y equals 5, 6. One thing I can do is, see, I can write this as x plus 2y, 3x plus 4y equals 5, 6, right? But notice that this, what I can also do is I can disassemble this and say this is x times 1, 3 plus y times 2, 4 equals 5, 6.
And then you can also do the augmented matrix representation.
But that augmented matrix is a technique that fits with any of these, right? This is the matrix form. This is the vector form, and x plus 2y equals 5 and 3x plus 4y equals 6 is the equation form.
What's that middle? Is that not the equation form?
This,
Yeah.
well, this is how you get
Intermediate
to,
step.
this is just an intermediate step.
Gotcha.
So you have 1, 2, three forms, and they're all essentially the same linear system. But you look at it in different
So,
ways.
The argument matrix, isn't that in there too?
It doesn't, it's just a part of the technology of Gauss's method. It doesn't, it's just a way of representing any of these systems. If I was given this,
Well, yeah, but those different forms are representing the same linear system.
but they're not a
Why-
representation in your system, they're just a graphical device. This is an actual, this is an equation, this is an equation, this is an equation, three different forms, augmented matrix is just a graphical device to solve the system. Okay, now I can say go from here to the augmented matrix, go from here to the augmented matrix, or go from here to the augmented matrix. The augmented matrix isn't really, it's just a device to represent this information.
I mean, aren't those forms different devices of the same information too? Like I'm feeling.
But these are equations, these are saying something.
those-
This is an equation, this is an equation, this is a couple of equations. They're propositions, they're true or false.
Okay.
The augmented matrix is just a device, it's just a matrix. It's just a representation of the information. The vertical bar doesn't mean equals, it's just separating,
Really?
it's just a matrix. This is not true or false. It doesn't, it's just a way to, like, you have X and Y's in all three of these. Right?
Yeah.
This
Okay.
is what's really going on. This one doesn't have the variables, the equal sign, it's just, or the matrices, it's just a graphical device that enables you to form the system. Yeah. So this is just a sort of a pictorial representation of any of these three.
So.
But any of the, but then what this means is, this says I have two equations, I want to find the solution set. This says, this matrix maps this vector to this one. We want to know what vectors get mapped. This one says, is this vector in the span of these vectors? If anyone's listening, this is just looking ahead. This has nothing to do with, don't worry about this.
So how would you do the matrix row operations on non?
Well, that's what we've been doing. You just do the row operations on the whole thing. I mean, you do the row like if you have 1, 2, 3, 4, 5, 6, and you do -2 row 1 plus row -4 row 1 plus row 2, 1, 2, 3, -1 times 4 plus 4 is 0. -4 times 2 is -8 plus 5 is -3, -12 -6.
Yeah, I know, that's what I'm talking about is the matrix form of that row operation. How do you do that?
Oh, this
Or you just keep using that.
oh, okay, so yeah, so if you, what you do is we
So
would
you-
form 1, 0, -4, 1, and then we multiply that by 1, 2, 4, 5, and we're going to get 1, 2, 0, -8, -3. So you see, you get that up there.
Yeah, yes. But I wasn't asking about that, I was asking about the argument matrix.
You don't do this with this.
Can't do that?
Well, I mean, the problem here is that that you haven't carried along. This doesn't do this. See,
So you can't do Jordan, you can't do Gauss's method using the matrix.
yeah, what's your, yes, it's misleading. It's like, what's this, you take, when we took the M's here earlier, this was just the efficient matrix, right?
Yeah.
So when I do this equals 1, I've left behind the 3 and the -6, right?
Yeah.
Now, I could, I suppose I could mock this up in the following way. I could do M minus identity times, like if I have M equals B, M X equals B, I could take it as MX minus identity B equals 0. So I could make, there might be a way to sort of make a new graphical device, a new device that would, but yeah, this is not quite, so I guess it's a little bit misleading. This allows you to solve homogeneous systems,
Yeah.
but mainly, okay, take care. Yeah, it's 150.
So if you knew that a matrix was not singular.
Then you can solve it
You could solve it by.
by finding the inverse.
You could solve it by taking the identity matrix that's in reduced echelon form. And then just do what you need to do to transform that matrix into your target, and then reverse that. That's interesting. You can go in that direction. Like,
Yeah.
You can solve it from either the original to the identity, or you can go from the identity to the original. And
Exactly,
both ways
exactly.
are good. I
If
feel
you're,
like going from the identity to that is easier to figure out how to go.
well, the thing is, you can, if you can realize that if you start from the identity matrix, you can take any row operations and you span out you get every non-singular matrix. Right? Because every non-singular matrix is row equivalent to the identity matrix for a given size.
I feel like that says something.
Well, it's like interesting, right? It's sort of,
Yeah, like I feel like that field of department brain that makes me think like I'm not seeing the whole picture.